Okay, so we're starting on page 259 this week. Wait, just kidding. We're starting on page 261 this week. We're starting 4-4. We're doing 4-4, 4-5, and 4-6. So feel like okay. So it says when a transformation is applied to a figure and then another transformation is applied to its image, the result is called a composition of transformation. A glide reflection is one type of composition of transformation. So a glide reflection is the composition of a translation followed by a reflection in a line parallel to the translation vector. So composition just means to combine more than one thing. So we learned all of the types of transformations last week. We learned that there's rotation, we learned that there's translation, and we learned that there's reflection. So a glide reflection is just a translation and a reflection put together. Okay, so the next thing says a composition of two or more isometries is an isometry. So who knows what isometry is? Yes. Reflections, translations, or rotations. So isometry is a transformation, right? A rigid transformation. Who knows what the word rigid means? It means that the shape will be the same size and the same shape. So the transformation doesn't change the shape or the size, but it still moves it. Okay, so we're going to write composition of isometries in our vocabulary. So remember at the top, write which notes this is. This is 4-4. Today is the 23rd, so 10/23/23 goes in on our date. Okay, and then our vocabulary goes in green, so make sure you switch colors before you do that. So composition of isometries. So a composition of two or more I'm just going to put transformations so we know what it means. And then I'm going to put rigid in parentheses is an isometry. Okay, so now we're going to do example 1. So example 1 is an example of a glide reflection. And again, example 1 is on page 261. So triangle PQR has vertices P11, Q25, and R42. Determine the coordinates of the vertices of the image after a translation along -4, 0, and a reflection in the x-axis. Okay. So in black, we're going to write our problem over here. So example 1, page 261. Okay, and it says we're going to apply the transformations we're going to do the vector -4, 0 and reflect over the x-axis to PQR. And then we're going to write the points. P is 1, 1. Q is 2, 5. And R is 4, 2. Okay, we're going to write the same thing over here. So apply the transformations. And we got the vector -4, 0. And we are reflecting over the x-axis. To PQR, where P is 1, 1, Q is 2, 5, and R is 4, 2. You're with Lorelei. Okay. All right, now switch to red for our work. Okay, so the way that we do these is we do them one transformation at a time. So we're going to apply the first transformation first. How do we apply a vector? Who remembers? The x affects x, the y affects y. So we're going to be adding this. So for P, we just take 1, 1, and we add the vector, -4, 0. Okay, and that will make P prime. So what's 1 minus 4? -3. What's 1 plus 0? Awesome. Okay, so we're going to do the same thing for each of them. So then we have Q is 2, 5. And we are applying the vector -4, 0. Okay, what's 2 minus 4? -2. 5 plus 0? 5. And R. Plus -4, 0. So R prime is just 0, 2. Okay, so now that we've done the first transformation, we need to do the second transformation. So I'm actually going to switch colors and do it in blue to show that there's a second step here. So now we're going to reflect, okay? So we're taking P prime and we're reflecting it over the x-axis. Who remembers what the rule is for the x-axis reflection? So the only thing with reflections is though it is reflecting over the x-axis, it changes the y, exactly. So the y just becomes negative. So our P double prime, after 2 transformations, is -3, -1. And then Q double prime is -2, -5. And then R double prime what is it, Heston? What's R double prime? 0, -2, perfect. Awesome. Okay, so this is our answer right here. So composition of transformations is the same thing we've been doing, you just have to do it multiple times. Okay. So we're not going to do example 2 because example 1. Let's do example 3. Okay, example 3 on page 263. Okay, it says reflect a figure in 2 lines. So, Nathaniel, you're with Heston. Heston's going to move back up to his seat so you can be with him. Thank you. Okay, so example 3 on page 263, it says reflect each figure in the line N and then the line Q. Oh, wait. Before we go to this, I want to talk about our compositions of 2 reflections. So, composition of 2 reflections can result in the same image as a translation or a rotation. So the composition of 2 reflections in parallel lines can be described by a translation vector that is perpendicular to the 2 lines and twice the distance between the 2 lines. Okay, what does this mean? So the picture actually helps us more than the words. So if we took P and we reflected it over this line, and then we reflected it again over this line that is parallel to the first, then it looks like it originally did. And so it's just a slide. And it's a slide of 2 times the distance because we reflected it twice, right? So there's 2 times that distance. So if you are reflecting over 2 parallel lines, then your vector of translation is going to be perpendicular. It's just moving straight across. And then the distance is twice the distance. Okay, and then theorem 4-3 is reflecting over intersecting lines. The composition of 2 reflections in intersecting lines can be described by a rotation. So this rotation is about the point where the lines intersect. So in this case, it would be about this point through the angle that is twice the measure or of the acute or right angle formed by the lines. So whatever angle is formed by the lines, the rotation is twice that distance. Okay. So that being said, we're going to do example 3. We're going to do it in the book and then we'll okay. I haven't decided if we'll write it down or not. So reflecting each figure in 2 lines. So this first one, is this going to be a rotation or is it going to be a translation? A translation, that's right. So we are reflecting over these 2 parallel lines, and the distance between the lines is 3/8. So how far is our translation going to go? If this distance is 3/8. What'd you say, Heston? 3/4. How'd you get? What do you do to get that? You multiply it by 2 because we are reflecting twice, 2 times. The distance is going to be twice that original distance. So 2 times 3/8 is 3/4. So the composition of 2 reflections is a parallel horizontal in parallel horizontal lines N and Q is equivalent to a vertical translation down by 3/4 of inches. Okay, and then the second one. So if this is reflecting over this line, and then, It's first reflected over this line, and then it's reflected over this line. It's actually rotating around the point of intersection here. And it's rotating twice the angle measure. So what would be the angle measure of the full rotation? 50 degrees. Okay. So we're not going to copy that one down. Sorry, didn't need to write example 3 on there. But we are going to do example 3's check. On page 264. Okay, and we're just going to draw the picture. So this is 4.2 meters. And has, just draw it to the best of your capabilities. Oh, yep, sorry. $264. Okay. So it says describe this as a single transformation. Okay, you don't have to write this one twice. Okay, if this is a reflection over two parallel lines, what can it be described as? Yep, on the same as 4.2. It can be described as a translation, right? So I'm just going to say using theorem 4.2. This is a translation, a horizontal translation. Left. How far? 4.2 times 2, right? So 8.4. 8.4 meters. Okay. I am going to put in green on the side of this, like a basic synopsis of what 4.2 says. So over here, I'm putting 4.2 reflection over a set of parallel lines makes a translation of twice the distance and perpendicular to the lines. So it's just a basic summary of 4.2. You can write yours however you want. Okay. The last thing before we move to the next section is we're just going to look at example 4 and example 5 on page 264. So example 4 says to determine congruence. It says, are triangle ABC and DEF congruent? If so, what composition of transformations can map ABC to DEF? So if something is congruent, you should be able to map it using transformations. Okay, what does it look like happened if we're going from here to here? What'd you say? A rotation. That could be. What if we reflect it first? So reflection and then a translation, right? Oh yeah, you're right. Or like Jen said, a rotation about a specific point, right? So you could do either of those where you reflect it twice and then a translation. Because this would be our reflection. Wait. Like that. And then you'd have to move it over 1, 2, 3, 4, 5. Or you could rotate it about the origin and then move it over 5. So whichever you want. Those are both valid answers. Okay, and then example 5 says describe the transformation that is going on combined with the pattern. So how did this pattern was created is what we're looking for. What'd you say? So if they look the same, it's probably a reflection over and over, right? If we reflect it over this line and then reflect it over this line. Or we could take this whole thing and it would be translational, right? So again, you can say multiple things to answer these. So the pattern is created by successive translations of the first and third design. So this pattern can be created by combining two reflections in a pair of parallel lines. So we just said it could either be reflections or translations, which is because they're being reflected over parallel lines. Okay, like I said, we're not going to write any of those, but we are going to move on to the next topic. So we're going on to 4-5. So new piece of paper. Okay, so I believe some of you did these in art. This is Tessellations. Yay. And this is page 269. And it is still the 23rd of October. Okay, who knows what a tessellation is? It says it in your book on page 269. Okay, it says the compositions of transformations can be used to create patterns from polygons. A tessellation is a repeating pattern of one or more figures that cover a plane with no overlapping or empty spaces. A tessellation can be created by transforming the same figure or set of figures in a plane. The sum of the measure of the angles around a vertex of a tessellation has to be 360 degrees. Okay, so this first picture is a tessellation of trapezoids. And what pattern are they using? What'd you say? Yeah. So they're reflecting them. Yep. I like it. Okay. So if you go down a little bit, it has some more information on tessellations. So a regular tessellation is formed by only one type of regular polygon. A regular polygon will tessellate if it has interior angle measures that are a factor of 360. Okay, so a factor of 360 means what? That it needs to divide evenly. The interior angle needs to be divide evenly into 360. So these could be 60 degrees, they could be 30 degrees, they could be 120 degrees, but they couldn't be like 75, right? Wait, does 75 divide evenly? Oh my gosh, I don't even know. Let's see. 360 divided by 75. Nope, 4.8. See, it's not correct. Okay. And regular tessellations mean regular polygons, meaning they all have the same size, or same size sides, okay, and same angles. Okay, semi-regular tessellation is formed by two or more regular polygons. The tessellation shown is made up of only equilateral triangles, so it is a regular tessellation, not a semi-regular tessellation. A tessellation can contain any type of polygon. A tessellation is a uniform tessellation if it contains the same arrangement of shapes and the angle in each vertex. Okay, so down at the bottom it shows you an example of uniform versus not uniform. So the four angles at each vertex have the same measure as the four angles at every other vertex. That's what makes it uniform. So if in this case, there are two angles at this vertex, and there are four angles at this vertex. So not every vertex is going to have the same amount. Okay, so on this one, we actually have quite a bit of vocabulary. So we actually are going to take up some of our problem space to write it. So we're going to write the basic one up at the top in vocabulary. So tessellation. So a repeating pattern of one or more figures that cover a plane with no overlapping or spaces. Okay. So down here we're going to put regular tessellation. And regular means it's formed by only one type of regular polygon. Okay, we're also going to say semi-regular. Tessellation. And is formed by two or more regular polygons. You're also welcome to put like a picture so you can remember. Okay, and then uniform tessellations. So they contain the same arrangement of shapes at each vertex. What'd you say? Sorry. Semi-regular says it's formed by 2 or more regular polygons. Yes, Tamika? Yes. Okay, so we're going to do example 1. It says determine whether a regular 16-gon will tessellate the plane. So example 1, page 270. Okay, and okay, so we just need, how can we do this problem? What'd you say? Yes, 16 dash gone. Sorry. Yes. So what are the rules for tessellation? So we have to find out the interior angles of a 16-gon. Does anyone remember how to find out interior angle? So equation for interior angles is 180 times n minus 2 divided by n. Who remembers what n stands for? In this equation? Yep. Number of sides or number of angles. Okay, so what are we plugging into this equation? $16, that's right. So we got 180 times 16 minus 2, all divided by 16. So I'm doing that on my calculator. 180 times 14 divided by 16 equals 157.5 degrees. Okay, 157.5 degrees. Why do we care about the interior angles? It has to be a factor of 360. So I'm actually going to add this up here to my definition. So angles, interior angles must be factors of 180, or 360, sorry. 360 degrees. So, this is not a factor, right? How can we decide if it's a factor or not? Yeah, if you divided it in a calculator, would it come out evenly? And in our case, it comes out to 2.2857, so no. So this would not tessellate the plane. What? Ooh, sorry. Okay. We're not going to write example 2, but it is really interesting to look at. So example 2 asks us to determine whether a semi-regular tessellation can be created from a regular octagon and squares that all have 4 sides 1 unit long. If so, how many regular octagons and squares are needed at each vertex to create the tessellation? So it says they tried to draw a pattern here. It says each interior angle of a regular octagon measures 180 times 8 minus 2 divided by 8, which is 135 degrees. And each interior angle of a square measures 90 degrees. The sum of the measures of the angles around the vertex of the tessellation has to be 360. So they make an equation that says 135 times x plus 90 times y has to equal 360. And they say let x be 2 to see if we can have 2 of those shapes or 2 squares at each vertex. So they plug that in, and y would have to be equal to 1. So a semi-regular tessellation can be created from 2 regular octagons and 1 square. So again, I think that this is just really interesting. So we're not going to go too much more into tessellations. Can anyone think of real tessellations, like tessellations in regular life? Like in nature. There's one sitting by Cayenne. A turtle shell has a tessellation on it. Sorry, a tortoise shell has tessellation on it. Also, honeybees, their honeycomb is a tessellation, right? So these things exist in nature, which is why we have them in mathematics. It's because somebody chose to chart them. So they do exist. When we lay bricks, that's a tessellation or tile. All right, the last thing we're covering is 4-6. So we're going to get a new piece of paper. And it is on page 275. Okay, so this one we're just talking about symmetry. We already know what symmetry means, but okay, so we are talking about lines of symmetry. So a figure has symmetry if there exists a rigid motion, reflection, translation, rotation, or glide reflection that maps the figure onto itself. The figures that have symmetry are self-congruent. One type of symmetry is line symmetry. Okay. A figure in a plane has line symmetry or reflectional symmetry if the half of the figure matches the other side. So this is what we are most commonly used to is line symmetry. It's reflected over some axis. This is even the type of symmetry that when you look in a mirror, it's symmetric across that distance between you and the mirror, right? So this is the type of symmetry that we're used to. And it says each half of the figure matches the other side exactly. When the figure has line symmetry, the figure can be mapped onto itself by a reflection in a line called the line of symmetry or axis of symmetry. Okay. And then the other type of symmetry is rotational symmetry or point symmetry. What? It might not be. We just have to identify if it is. Okay, so a figure in a plane has rotational symmetry or radial symmetry if the figure, this is on page 276, if the figure can be mapped onto itself by being rotated less than 360 degrees about the center of the figure. So the image of the pre-image are indistinguishable. The point in which the figure can be rotated onto itself is called the center of symmetry or the point of symmetry. This figure has rotational symmetry because the rotation of 90 degrees, 180 degrees, or 270 degrees maps the figure onto itself. So the number of times that a figure maps onto itself as it rotates from 0 to 360 is called the order of symmetry or the magnitude of symmetry. No, the magnitude of symmetry is the smallest angle which the figure can be rotated so it maps onto itself. The order and magnitude of rotation are related by the following equation. Magnitude equals 360 degrees divided by the order. So the figure has an order 4 and a magnitude of 90 degrees. So we can rotate this diamond 4 times to make the same diamond. And if we rotate it 4 times, that means we're rotating it every 90 degrees, okay? Okay, let's write some vocabulary. Okay, so line symmetry is reflectional symmetry over an axis of symmetry. And then we're going to say point symmetry let's see, what's a good way to say that? Is rotational, where the picture will be identical when rotated around the center. Ooh. Oops. And I forgot to put at the top that this is 4-6. It's on page 277. Okay. So example 1 says to identify line symmetry. And I'm just going to draw the pictures. Page 275. Okay, so for A, we just have a regular pentagon. I'm just drawing a house over here. So how many lines of symmetry does it have? So we have this one. Are there any others? Right, this wouldn't work. Right. What if we did it this way, through the middle there? You could do the same one at every vertex, right? So 5. 5 lines of symmetry. Thank you, Nathan. Sorry. Of course, my picture looks atrocious, but that's okay. Okay, so B, is B symmetric? How many lines of symmetry does B have? Right? It is not symmetric. It is not able to be folded and mapped onto itself. So 0. Exactly. Okay. And then example 2 says identify rotational symmetry. We're not going to draw this one out. So objects found in nature often have rotational symmetry. Determine whether each one. So does this have rotational symmetry? No, right? You can't rotate it and make the exact same shape. It almost has, it's probably pretty close to being line symmetry though, right? What about this one? It does. How many? 1, 2, 3, 4, 5, 6, 7, 8, right? So this 8 order of, and then the magnitude would be what? Magnitude is degrees, so 360 degrees divided by the order. So 360 divided by 8 is 45. So it has an order of 8 and it has a degree or magnitude of 45 degrees. So every 45 degrees that you rotate it, it will be identical. All right. Does anyone have questions on what this stuff is? Okay, put your guys' notebooks away.